A blizzard can erase a trail quickly. An interior Alaska Athabascan hunter several miles from camp could still know the direction home and lose every landmark that confirmed it. Snow hides river bends, low ridges, and the marks left by his own snowshoes. Wind carries heat away from exposed skin. His hands lose precision while every step costs more. The only building material within reach is the loose snow you see under his feet. Before visibility closes completely, he stops, turns that snow over, and begins raising a mound. You can see why continuing toward camp still feels rational. Walking produces heat, and the destination already exists. But that plan depends on visibility, recognizable terrain, and physical reserve. The storm is removing all three. A wrong turn adds distance. Deepening drifts increase the work of each step. Damp clothing loses part of the air that made it insulating, while wind continues replacing the thin layer warmed beside the body. By the time the hunter knows he is off course, his hands may no longer manage straps or tools cleanly. Stopping early preserves the strength needed to build. Stopping late leaves only the need. Disturbed snow does not behave like the loose powder around it. Each step, strike, or push breaks delicate crystal branches. Smaller pieces settle into the spaces between larger grains. The mound loses volume, becomes denser, and offers the wind a more continuous surface. Follow the air, and you can see it pass around the compacted mass instead of through loose powder. That changes the immediate thermal problem. Outside, moving air continually replaces air warmed by the hunter's body. Behind the mound, that exchange slows. He is not heating the storm. He is protecting a small pocket of stiller air from it. The mound is not yet a shelter, but it has reduced the wind's direct access to his clothing and skin. Now the material creates a new problem. It cannot be hollowed as soon as it is piled. You would see the hunter leave the mound untouched and limit his movement. He remains exposed, so the pause has a cost. Dig too early, and the new cavity may slump inward. Keep working without control, and sweat and fatigue consume the reserve the shelter is meant to preserve. The mound must change before the hunter can safely remove its center. When the surface finally resists his hand and holds its curve, he opens a narrow passage near the base. Every armful removed creates room, but also removes support. He hollows only a body-sized cavity beneath the packed shell. Snow from the center goes back outside instead of thinning the roof. Trace the wind with your eye. The storm now crosses the mound rather than the place his body will occupy. Excavation turns the windbreak into a chamber, but the protected air reveals another heat path. The chamber stays low because size has a thermal cost. A larger hollow contains more air and more interior surface for one body to affect. In the smaller space, breath and metabolic heat influence the air nearest his clothing before that energy crosses the wall. The snow creates no warmth. If you follow the heat path, it only slows the replacement of warmed air by the storm outside. Once that exchange is reduced, the coldest continuous contact is no longer beside him. It is beneath him. The wall works as a porous boundary rather than a solid block of ice. Heat can travel through the ice skeleton, through air in the pores, and with water vapor moving across those pores. The exact rate changes with density, temperature, and grain bonding. That is why you cannot assign the chamber one promised interior temperature. Its advantage is a slower loss rate and an absence of direct wind, not a warm room. Snow compressed under the hunter's back and legs carries heat into the floor. A dry ground layer interrupts that contact. Athabascan records describe spruce boughs placed on snow and on tent floors to keep people dry and warm. Inside this chamber, boughs or carried bedding, if available, would serve the same physical function. Crossed branches and trapped air keep fabric or hide from lying flat against the snow. The exact material can vary. The thermal requirement does not. That separation lets the chamber address two losses at once. The wall reduces wind-driven exchange around the body. The ground layer reduces direct conduction below it. At human scale, you can see the consequence. Hands remain useful for adjusting clothing, eating, and protecting the entrance. Yet the passage that admitted the hunter is now the weakest part of the boundary. The ground layer also protects the hunter's clothing from the surface, where pressure and body heat can concentrate moisture. It cannot keep every layer dry, and it does not replace insulation worn on the body. Its value is narrower. It prevents the floor from bypassing the calmer air and drawing heat directly from the largest areas in contact with the snow. Once that path is reduced, the entrance becomes the dominant opening left to control. A broad opening would let gusts replace the air he has begun to warm. Sealing the chamber completely creates a different danger. Breath adds carbon dioxide and moisture to a small volume, while drifting snow can narrow its connection to the surface. The passage must restrict direct wind without becoming airtight. Its exact shape cannot be treated as one fixed Athabascan design. When you trace the air path, it must still connect the chamber to the outside. Warm, damp breath then reaches colder snow. Some moisture can freeze onto the inner surface, while some remains in clothing and bedding. The shelter has not removed humidity. It has confined the place where humidity matters. Dry layers continue holding insulating air. Damp layers conduct heat more readily and become harder to manage as hand control declines. Solving the wind problem has created a moisture problem inside the protection. What you see on the inside surface can therefore become firmer or frost-coated while the air remains below freezing. A smooth, cold wall does not mean the shelter is warming itself. It means vapor has reached a boundary cold enough to freeze. The hunter still has to keep bedding away from wet patches and avoid unnecessary exertion. The mound has changed which problems dominate, but it has not removed the need for careful clothing and moisture control. No large fire drives this reconstruction. A flame in such a small chamber would add smoke, melting, and much greater ventilation demands. The heat source is the hunter's metabolism, supported by food and protected clothing. What you do not see is the density trade-off inside the thick wall. More compact snow carries structural load better, while very loose snow usually conducts less heat. The shelter needs enough compaction to stand, with enough pore space remaining to slow heat flow. That balance is visible in the wall, but produced at a scale too small to see. The freshly disturbed mound first yields and slumps. As grains remain in contact, ice bonds grow between them. The shell becomes harder to penetrate and better able to hold its curve above a hollow. Snow scientists call this process sintering. The hunter can test the result with his hand, but if you watched only his movements, the structural work would remain invisible. The waiting period was not a delay after construction. It was part of construction. If overlooked engineering like this deserves careful attention, subscribe and keep following what the material itself reveals. Athabascan families in interior Alaska also carried skin tents when they moved from winter houses toward hunting and trapping grounds. If you compare the boundaries, a carried tent answered the same weather with a different exchange. It could be raised without waiting for snow to bond, and its shape arrived with the travelers. But a thin skin boundary had far less depth than a packed snow wall and depended on poles, coverings, and bedding brought from camp. You can see the trade clearly. The snow chamber exchanged portability for local material and thickness. It required suitable snow, labor, and time before excavation. The skin tent exchanged wall depth for speed and predictability. Both had to control wind, ground contact, and moisture, but they solved those variables with different materials. You cannot make either shelter universally superior from that comparison. It shows why a hunter without the carried structure might turn the snow already surrounding him into a temporary boundary. A tent also separates the traveler from falling snow before a mound could be built. The snow chamber becomes most relevant when the carried shelter is absent and enough workable snow is present. That limitation matters because you cannot treat the technique as a universal answer to every blizzard, every snow type, or every stage of exposure. It is a material response available only while the hunter still has the strength and time to reshape the snow. The storm still moves over the mound at full strength. Snow gathers around the entrance. Wind presses against the shell, and the route toward camp remains hidden. Inside, the hunter does not become comfortable. He becomes less exposed. Clothing and bedding still provide most of the insulation. The chamber gives that insulation a smaller, calmer environment in which to work. When visibility begins to return, he clears the opening and reads the terrain again. The chamber has not shortened the distance home. It has preserved the judgment, hand control, and physical reserve needed to cover it. This reconstruction draws on winter knowledge presented in an interior Alaska Athabascan curriculum, where building a mound-and-hollow snow shelter is recorded as a traditional survival skill. The credit belongs to the communities that taught how snow changes under pressure, how a temporary shelter fits into winter travel, and what a body needs when the route home disappears.